Boosting is one of the most successful methods in building ensemble models. In boosting, there is a sequence of models being built, each attempting to improve or to boost the performance of the previous ones. Each new model gives more weight to the data points where previous models made errors and tries to learn them better. This is different than bagging, where the base models are independent of each other. There are two types of boosting algorithms: weight-based, such as AdaBoost, and residual-based or gradient-based. The original boosting algorithm was proposed in 1990, and the objective of this algorithm was to train 3 models, and they would work in tandem in the following way. On each new data point, you would have the output of the ensemble model being given by the first 2 models if they agree on their output on that data point. If they disagree on it, then the third model is going to give it. And here is the strategy of how to build and how to train these 3 models. Your dataset X is being split into 3, X1, X2, and X3, and you start by training a model, the first model, on just X1. And after you've done that, then you're going to check the accuracy of this model you've built on this training dataset, and you will see that on some of these data points there are errors, and I'm indicating this with this sort of gray dashed area in X1. So that's the area where M1 made errors. And then you are also testing M1 on the second part of your dataset X2, and you discover that maybe M1 is also making mistakes on some of the data points in this X2. And then you start thinking about model M2, and remember that the idea is that you would like M1 and M2 to agree as much as possible. So the idea of M2 is that you would like to show it these data points where M1 was correct, because you would like to encourage M1 and M2 to agree on data points. But also you would like to do better than M1, so you're also going to feed to M2 these data points where M1 was not good enough. So in other words, you are going to train M2 on some of these data points where M1 was correct, but they were not used to train M1, but you want M1 and M2 to agree, so you will feed these to M2, and also you would like to improve on M1, so you are feeding also these ones to M2. And then you are going to test on the third part of your dataset, you are simply going to test if M1 is equal to M2. And you will discover that on some of the data points, indeed, they agree, and on some of the other ones that I'm indicating with this hashed pattern, they disagree. And then finally, the last step in your ensemble model is that you are going to take these ones where they disagree, and you are going to train the third model just on these points of disagreement. And all of these things are done with the focus on this objective we have, that M1 and M2, if they agree, they are giving the output of our ensemble model. If they disagree, then it's going to be given to M3 to have the deciding vote and to give the output on that model. This boosting algorithm turned out to be quite successful in improving the accuracy of the base models. And even if you have relatively weak learners that are better than random, but maybe not significantly better than random, this sort of boosting algorithm is going to do well, and it will give a much stronger model than the original one. One major problem with this sort of with this original boosting algorithm is that the data set has to be very large, and the reason for that is that you see, you have the strategy of splitting them into 3, and you build your first 2 models, and the third one is only going to get this small part of the data set, of the third part of your data set, on which the first 2 models don't agree with each other. And so the point is that if you want to be successful, you've got to have enough data points to train this third model M3, and for that you need to have a very large data set to start with. And that can be problematic depending on your application, and so this idea of the boosting algorithm has evolved, and then later on there was this proposal for a different sort of boosting based on weights, and the first form of this sort of an idea was the AdaBoost algorithm in 1996. This algorithm has by now quite many different versions, especially with a focus on how to calculate the weights from model to model, but the general concept is the same. The objective is to generate a sequence of base learners, and not necessarily just 3 models as we had in the original boosting algorithm, but you can have as many as you wish. So you generate a sequence of models, and each one of them is going to focus on the previous model's errors, and is going to try to improve on those errors. So here is a demonstration of the concept. Let's say that we have a data set, and you have this model that does a stochastic sampling on the data points in the training phase. And in the beginning, I mean, for the first model, you don't really have any preference for selecting different data points with different probabilities or weights. And so in the beginning, very typically, all of them have the same probability of being selected for the training phase or for the epochs of the training phase. And then you train your first model on this one, and then you check on which data points this model has made errors. And then the concept is that on those data points where you have errors, you are going to increase their probability to be selected in the training phase of the next model. So in other words, the next model is going to focus quite much more on the data points on which this first model is making errors. And so for the second model, we are going to update the weights, and you are going to have some of the data points having more weight than the other ones, and these are exactly the data points where the first model was making errors. And the concept now becomes this: you had errors on this data point on the first model, so let's try to have this model focus pretty much on these ones. There is a chance also for the other data points to be selected, but they will have a significantly higher chance of being selected for the training phase of this second model. And then you've trained your second model, and then again you are checking, you are updating your weights so that you give higher weight, higher probability to be selected to the data points on which this model is making errors. And so, for example, in the third round, you could have the weights updated in this fashion, and these are data points on which this model has made errors. There could have been also some data points like maybe this point 19 on which there was no error previously, but maybe this one has made an error. So this is going to be reflected now in the third round. And some of the other ones on which this one still didn't manage to improve, they will have even higher chance of being selected than we had in the second round. And this continues in the same way. You could have in the fourth round, again a boost in these probabilities. And so the concept is this, that each model is going to focus more and more on the data points where you have errors in the previous models. So here is how this is done. I'm showing one version of this algorithm, and again there are many different versions of this algorithm, especially with respect to how to update these weights based on the previous models. But here is one version of this one. You have your data set and you initialize the probabilities for these data points to be selected to be equal, and it's just 1 over the number of data points in your data set, and then you will have a number of models that you are attempting to train, and for each one of these models, so for each iteration, you are going to randomly draw a data set from this initial data set you have, but you are going to use the probabilities that have been updated in the previous iteration. So in the beginning they're all equal, but you will see in a moment that they get updated. So we randomly draw this one with these probabilities, and we are going to train our current model on this data set that we've drawn. And then after we train, we make a prediction using this model on the data point xt, and we're going to calculate the error rate. And if we see that the error rate in fact is larger than 1 over 2, meaning that this model is really worse than random guessing, then we are going to stop. There is no sense in continuing it. It looks like this is as far as we could go with this strategy. But if this is not the case, this model is still quite good, then we are going to think about where are we making errors and how to update the probabilities of those data points where we are making errors. And so we are going to focus on this beta, on this parameter beta j, and for example, this is not the only way to do this, but for example, it could be calculated as the error rate divided to 1 minus the error rate. And another way to think about this is that this is 1 minus the accuracy divided by the accuracy of the model. And the point here is that you are going to update the probabilities in the following way. For each data point, you are going to decrease the probabilities if they were correct. And so you are going to say, if the prediction of the current model is exactly what it should be, then I'm going to decrease the probability of this data point to be selected in the next round. Otherwise, I'm just going to keep it unchanged. And then we normalize the probabilities, so we just have the usual normalization so that they sum up to 1, and we continue with this cycle. And so at the end, we've got our sequence of models, and if we want to apply this ensemble model on a new data point, for example, in the testing phase, the way this goes is that given a data point, we are going to calculate the outputs of all of these models on this data point, and then depending whether this was a classification problem or a regression problem, we are going to combine these outputs to get the overall output of the ensemble model. So a few points to make about this type of AdaBoost algorithms. One is that you have to think about the base models, and in that sense, it's a very flexible type of algorithm, because in the base model you can have anything you like as long as you can give it weights in the sampling of the data. But other than that, you can use whatever algorithm you want, whatever model you want to have, whether it's a classification or a regression problem. You have to set the maximum number of estimators for the ensemble model. That's going to be your stopping step when you've reached the maximum number of base models or estimators you wanted to have in your ensemble. The other stopping is when you got an error rate that's larger than half. So the models got worse than random guessing. And the other point I want to make here is that there is also the concept of the learning rate. And the thing here is that you may have a learning rate between 0 and 1, and you could apply this learning rate to the contribution of each of the boosting models to avoid overfitting. So the idea being that you could use a learning rate of, say, 0.1 if you like, and each consecutive boosting model will only contribute a percentage of its output to the overall model. And if you, I mean, one way to think about this is that you are somewhat conservative. You would like to take into account this boosting, but maybe not go all the way, but just give it a little bit of a nudge in the right direction, but not take it all the way, just so that you are avoiding overfit. And if you, just one rule of thumb, if between attempts to train such an ensemble model, you think about increasing the number of estimators, then a good idea is to use a smaller learning rate as you are adding more estimators. There is also the possibility of using a learning rate equal to 1, and then you are taking the contribution of each of the boosting models as they offer it. Here is an example of how to use AdaBoost with Python and sklearn. You can import the AdaBoost classifier if you have to do a classification problem. If you work on a regression problem, you are importing the AdaBoost regressor, and then you just create an ensemble model using this function AdaBoost classifier. There is the function AdaBoost regressor for a regression problem, And to this function, you can pass the type of base model you want to use. In this example here, I'm just indicating a decision tree classifier. And you can pass the number of base models you want to have. In this example, I'm indicating 100 base models or estimators. And you could also indicate random state, and there are a number of other parameters that you could also set. Now, once you've declared this one, then you can just fit your model on the data set, and then you can use this model to predict the output of a new data point in this way. Now, the other type of boosting is residual-based, or this is also called gradient boosting. And the difference here is that the focus is going to be in this type of strategy on the optimization of the loss function. You are going to take a look at what's the loss function, in other words, what's the difference between the real value of a data point and the prediction of the model you already have in your hand on that data point, and you are going to try to improve on this loss function. So this difference between the real value and the predicted value, that's going to be the value that you are going to use for training your next model. So what this means is really that each new model in the ensemble is going to be trained on this sort of a negative gradient of the deviance loss function. So what this means, once again, is this one. If you think about the first time you are adding a model to your ensemble, so the first boosting model, you are going to take a look at the difference between the real value and the prediction of the base model. And this difference is going to be the data set on which you are training this first boosting model or the second model in your ensemble. So the point here is that you would like to optimize on this difference between what it should be and what it really is in terms of the predicted value. And you do that, and you continue in the same way for the next models. When you are in the nth boosting model, you are going to train that model on the difference between the real value and the additive predictions of all the previous models. So the point here is that all of the previous models, the original one that was trained on the original dataset and all the other ones that try to improve on this difference between the real value and what you got so far, they get added together and they together contribute to the output of your model. Also in this case, we have the concept of a learning rate with the same objective that you would like to avoid overfitting. And again, the point is that maybe you don't want to take the full contribution of each of the boosting models, but you would like to take just a percentage of that. And that's exactly what this learning rate is. It's just curtailing the contribution of each boosting model to avoid the overfit. An example of code, how to use gradient boosting in sklearn and Python. This particular method in sklearn is using decision trees as the base model, but you can use this both for classification and for regression problems. And the point here is that you are going to declare your gradient boosting model using this function for a classification problem and using this function for the regression problem. And again, there are a number of parameters that you can pass to this. For example, you can set how many base models you want to have. You can set the learning rate. These are in the base models. Remember, these are decision trees. So you can set how deep you want your base models to be, the random state, and lots of other parameters that you could set on this. And once you've declared this, you just fit your model using this function. Once you fit your model, then you can use that model to calculate the score of the model on your data set. You can also use the predict method to calculate the output of this model on a new data point.